Good afternoon. My name is Saramon Chaichan from Suratnari Vidya School. Now I am a reporter.
Hi, I'm Nalinda Liye and from Lala International School, and I am the opponent.
Good afternoon. My name is Banawit Pimpanuwat and I am a reviewer.
Okay, the problems. The thing that the problems want from us is to optimize the system to produce the maximum angle. So from this, I make my flow diagrams, solve the interpolate the problems, investigate, and the thing that I found from investigate is height, ball mass, and the spinning. Then I made the free body diagrams, made the experiment to find the relation between R and theta, and find the relation between theta and K, which K is a spatial ratio that I will show you in next page. Then I have the data, and made the data analysis, and finally, I made a conclusion. Let's start with the theory. The first one, in this case, is the approximation, so it's easy for the calculation. In this case, it's the direct airstream. We have the weight of the ping pong ball and the drag force. So we get this. Fd is equal to 1 over 4 low with zeros to the power of 2a. And I get this as the equation 1. So this is case of the tilted airstream. First, we should know the natural of the airstream, which is, okay, it's like a triangle from the axis nozzle. We have V0 on the center and have V1 and V1 on the border of it. So when we tilt, in this case, there will be a drop angle, which is theta 1. And to make the ball be in the stable ball position, there's be other force act on this ping pong ball, which is caused from the difference of the pressure. So when I divide the force into different way, I have found finally of the equation, which is Fd cos theta 2 plus Fp sin theta 2 is equal to mg. To hold this up, and Fp cos theta 2 is equal to Fd sin theta 2. From the equation 1 about the drag force, and for the Bernoulli principle, I found about the delta of P, which is equal to 1 over 2 low with 0 square minus V1 square plus low GH. But in this point, I will ignore about low GH. And Fp is equal to delta PA. So when I get this equation final into this one, I finally get this long equation. If we see from this equation, there is 3 main variables, which is V1, theta 2, and V0. So I want to make it become in only 2 variables. So I define K as a ratio between V1 over V0. And then I move the side of the equation, which is V1 is equal to V0K, then put it back to the equation. And finally, the equation is sin theta 2 minus 1 over 8 cos theta 2 k to the power of 2 minus 1 over 4 cos theta 2k plus 2 minus 1 over 8 cos theta 2 minus sin theta 2 is equal to 0. It's a quadratic equation which relates of the maximum angle theta 2 and the k constant. So from that equation, I get it and make a plot to find the trend of the graph. Then the thing that I found is to make the equation output to be zeros. The lesser in the k value will form the higher maximum angle, which case that as a ratio between V1 over V0. Another thing that I get from the observe is the spinning. You know, at the normal direct airstream, the pattern of the spinning is kind of irregular because I think there will be a little bit error of the velocity from 2 sides. But when we tilt it, I see more obvious pattern of the spinning, which is faster and faster because there is a drop angle. So from that drop angle, there will be difference in the velocity. The difference in the velocity will make the difference in force. And it will cause higher torque and spin faster. It will spin fastest at a height before it falls down. For the experiment to form the maximum angle, first, I would like to find the relation of K between R and theta. From this is the dorsal axis, and this is V0, and this is V1. The thing that I want to know is how V1 is related in the function of R and theta. Okay, so I made the experiment setup, which is I use the small turbine, then make some kind of sign on it, and I adapt the harp circle and the ruler together to set up. You see this is a small turbine, a little bit here. So I will move it, and then I use the high-speed camera to shoot it and get it to make a data analysis by using tracker. And this is the velocity that I found in the unit of left per sec. The thing that I would like to show from this data is the velocity at 0 degrees and have the smallest value of r, have the highest of velocity. And for the highest of the angle and the farthest, make the lowest velocity. From this, I want to find the relation of k. So I get this velocity to make the ratio between this velocity. And this is the k of, this is the value of k, which is related with the maximum angle. Well, this is the graph that I plot, but this graph is offset. So it makes you be able to figure it out that this is ratio of 1, 1, 1 in different height of it, the ratio of it. When I put the graph together, well, you will see that at this point, this is the value of the k, and at this point, is about this. Okay, how to use this table? First of all, I make, okay, theta 2 is equal to, theta 2 is equal to theta 1 plus theta 0. And the theta 0, we observe from this, theta 0 is equal to this part. And theta 1 is equal to alpha 1 plus by alpha 1 plus alpha 2, which alpha 1 is mostly equal to zeros. Then I divide by 2 to become the theta 1. And the alpha 2, and sorry, this is wrong. And if we know the value of the alpha 2, we will put it back and see from the table, and we will find the value of k, which I will make a calculation at a final to show you. Now, we'll consider what factor is related with the maximum angle. The first one is related with the k, the constant, the k, the ratio. The first one is the size of the dorsal axis. The second one is the mass of the ping pong ball. And the third one is the pressure. If the different pressure, this time because it's different, so the thing that relate is about the ratio between small h and high h and about the turbulence. So let's start with the first one, which is the side of the dorsal axis. If I set the pressure as 5 psi and the mass, which is 2.6 grams. The first one is the surface radius is 0.3 centimeter and the maximum angle is 35 degrees. But this one is a bigger one, which the radius is 3 centimeters and the maximum angle is 35 degrees. From the experiment, I came out with this. This is the trend of the graph of the value of k. From this, because it's the small of the nozzle axis. So it will be a large difference between V1 and V0. This is V1, this is V0. So the value of K will be very small. The small value of K will make the maximum angle big. In contrast with this case, V1, because it's big, so V1 is very near to V0s. So the value of K, which is the ratio, is very big. So the maximum angle that it can form will be very small. For other parameter is the mass of the ping pong ball. How can I control the mass? I use the push pin to get it, and I use the hot glue and rolling it around. From this, you see that the smallest mass of the ping pong ball will form the highest maximum angle. This is the trend of the graph that the more in mass will create less maximum angle. Why? Because if you came back to the table of K again, you will see that if the mass is lower with the same pressure, you will see that the R will become higher. And the higher in R, it will make the value of K become lower. From this, you see the trend of the information. So finally, the less in mass will make theta 2, the maximum angle, become very high. For other parameter is the pressure, which I set the mass as 2.6 gram and R of height at 0.3 centimeters. From this, the thing that I see is the first pressure that be able to maintain the ping pong ball can form the highest maximum angle. I think there are two related reasons why it be like this. Because the first one, from the observe, this is the first edge on the direct air stream. And this one is its edge, or from the path of the table of K is R. It become higher. So I make a measurement and came out with this. You will see that the more value of the ratio of h, small h over big H will form the highest maximum angle. And other thing that relate is also about the turbulence, because from the calculation, this one,
Right, so I just wanted to ask, the main thing that caught my eye was when you changed the mass of the ping pong ball, you said you rolled it in glue, right?
yes, I stab it and then I put a hot glue in it and roll it.
Yeah. So you mean the glue is actually coating the inside of the ping pong ball?
Yes, it get inside, but the properties of the hot glues, when we get into it, we roll it. When first time it hit the surface, it will dry, and it's not affect the center of mass.
But how can you be certain of that? Because you can't be sure that it will cover the inside smoothly, if you know what I mean. Because you can't really control and smooth out the glue. It might be sort of gathered at a point, and that could change the center of mass.
Yes, well, after the after the experiment, I cut the ping pong ball and I felt that inside is smooth. But I admit that there are some kind of problems about when we put too much weight on it, the glue will not dry, so it will affect the center of mass. But from that, I don't use that much mass to make the experiment.
Could you please go to a slide that was about the mass, that compared the mass and, right, so, okay, I see. But, so you said there wasn't much, how to say, from what point was there like, where glue wasn't as dry as it should have been? I understand that you said that there were some times where the glue didn't dry completely.
Completely dry. You want to know which mass is the maximum mass that it can dry or
Yeah, like just so I have a comparison in there.
well, from my experiment that I cut a ping pong ball, 4.2 is the maximum. More than that, it will have a problem.
Which is why you stopped. So then do you think that it's possible that that might have affected the rotation at all?
Sure.
And do you think what do you think the rotation actually does again? You said it stabilizes it, right?
Yes.
But what is your definition of stable?
My definition of stable is the center of mass is on the same level of height.
I'm not sure I follow. So,
The
can you just
center-
define, like maybe draw it on there or something?
Okay. The definition of, you asked me about the definition of stable.
What you considered was stable
Stable.
for the ping pong ball when it was in the airstream.
The meaning, the definition, in my definition term of the stable is mean the center of mass of the ping pong ball is on the same level of height. You know, even though it's rotate or moving, the center of mass is still the same.
So you mean it doesn't move? It's kind of just at the same level.
If you put in the same height of, if you put in the same, is the appropriate height, it will not moving. But if you put, maybe, it should be, maybe, if it should be in 11 centimeters, but when you start, you put it at 5 centimeters. From my experiment to find the velocity, you see that the more it close to the pipe, it will have more velocity. So it's not tendency. So it will moving up to reach this point.
I see. So it's stable when it has moved up to the point where it
Yes.
won't go down anymore. Okay. And they were all different for the different mass what do you call ping pong balls? Was there any how to say difference in rotation of like different mass ping pong balls?
I think, yes, it's different because different mass of the ping pong ball will affect the different height, and the different height will be affect from the K value. And now the difference between the velocity, the rotation caused from that difference of the velocity. So different height will cause different ratio of the velocity, so it will affect the rotation.
Yeah. Okay. So, oh yeah, there was a thing when at the setup. Can you please go to the setup slide?
Okay.
Because, right, I wasn't sure I quite followed your setup. So I understand that
Okay, I will explain it.
because yeah.
Okay. Okay, this is my setup. Well, this is a small wind turbine,
Yeah.
which it can move. I put it with a broken lamp that I don't use it,
Yeah.
and it can move. So with this half circle, I apply it with the ruler. I will measure from this point that, okay, I want 11 centimeters from how many theta, so I will fix it, I will label it and get this lamp into this, and then I let the turbine flow, and then I use the speed camera to catch it. then make the data analysis in left per second.
So the turbine is to find the speed of the wind.
Yes.
Well, because I noticed that in your graphs, right? You have this sort of sharp, that kind of
Yeah.
shape, right? That means that in different places it's got different speed, right?
Yes.
But I wanted to be, how could you be sure that you were measuring at like the absolute correct point? Because we know that the speed it sort of varies. It goes. You've got like this straight out sort of area. Then the speed sort of slows down.
Yes.
It's different. The velocity is different at when you get wider. But how could you be sure you were measuring like at like precisely the middle and precisely?
Well, that is a good question. I do it multiple times.
Oh, so
So,
it was like
yeah.
you estimated that
Yes, it's
that this
estimated.
is and
I think does not affect too much.
oh, okay. And oh well, for the turbine, you know the turbine, just like how big is the turbine actually?
It's very small. The radius of it is about 0.45 centimeter, very small.
Okay, so how did you actually track it? I mean, because
Track. Okay, I will show you.
Okay.
Well, when I have the video file, I will get the camera in the top side of the direction. Then I make some label on it.
the black spot, right?
Yeah. And yes, this is access. I will slow the clip down and then I track this manual tracking because no, because there will be a problem that there is a shadows of the pencil, and the shadow of pencil it will make the other tracking confused. So I need to make a manual track about 100 times.
Okay. No, because like originally I didn't understand the reason it was there for, but I understand now. I'll just go straight into summarizing then. Okay, so in her presentation, she talked about she had an equation to how to actually find the maximum angle that you could put a blower at for the ball to remain stable in the airstream. And she talked about there were a lot of graphs that did explain what she meant, explain what she saw too, with the airstream particularly, and she then explained a lot of what I felt was unclear in the experimental setup when she was explaining it, and yeah.
So, as a reviewer, I will start with the reporter. Her strength is there are some free body diagram that you can see that how many forces that related with this phenomenon, and then she did a profile about the velocity at different distance from the nozzle and at a different position. And her approach and the experiment is very quantitative, and I think this is her good point. But when we talk about the drawback of her presentation, you can see that she didn't define some words that very important in the problem, and she didn't tell where the FP and like FD drag force come from. And as you can see in the slide that she tracked the turbine that are spinning. I think it is a rough velocity measurement. It will be it will have many errors in it. And about the presenting about the data, you can see that her table is, have a lot of numbers, and sometimes the viewer can follow when she presenting. And as something like the experimental setup, she didn't explain it clearly. And the last one is the problem said that you have to optimize the system to produce the maximum angle, and I didn't see that she do it or not. And let's move to the opponent. That her strength is she asked about the hot glue cover smoothly in the ball when when we put in it and roll with it smooth. That I agree with the opponent here. And about the stable ball position, as I mentioned at the beginning, that the reporter didn't say anything about a stable pole position. So when the opponent asked about this, I totally agree that we have to know how she think about the stable ball position. And the air velocity is precisely measured. So at first, she didn't tell us about how she measured the velocity. She just tell us that she used this turbine and then roll the wind flow, and I don't know how she track it. So I think I agree with the opponent here. But the weakness is at the beginning of the discussion time, the opponent focused too much on the rotation and didn't go anything like just ask and nothing more. Didn't go further than that. That is there anything else about the rotation? And she didn't ask about the theories at all. The forces, the why she tried to explain that way. The opponent missed about this point. She focused on the experiment too much. Thank you.
You go to slide 16 and 17. Yeah, can you clarify these two graphs a little bit? 16 and 17.
You want me to clarify it? Okay. Well, from the figure, you see that I want you to figure it out. So the graph that I make is the offset graph, that it starts with the beginning in each point. And you see that this is the data of the K, which is K is a ratio between V1 over V0. You see that this is reached the highest point. Offset graph is mean I compare between all these 4 points to this point. But I want to show to you in the different height of it.
You not compare different line, right? You compare the same line,
Yes.
the same set of the data.
Yes, in this part.
Okay, that's why you mean the offset.
Yes.
So in the center, it should be the same point. Actually, it has the same point, the same K value, right? which is 1.
Yes.
Okay. And how you determine the angle? I mean, from your data, you go up just to 12 degree, right?
Yes.
Why no further than that?
No further than that because I have tried further than that, and for the shape of the stream will be like this. And if I go further than the 12 degree, it can be measured here, but it cannot be measured here because it will out of the stream, of the angle.
So this is the limitation of your setup,
Is it limit?
right?
Yes.
So I saw the graph, the trend graph on your slide number 9. Can you go to that page?
9.
Yes. That's the y-axis is the k, right? And the x
No,
is the maximum angle.
No, y-axis is the output of the equation. Okay. From this, you see that the output of this quadratic equation is 0. So I make a graph that this line is the equation output is 0. So the maximum angle, and I set k as a different number, is like random to see the trend of the graph. Then the point that is cut, the line cut each other is the maximum angle that it forms.
So you're predicting that the maximum angle would be about 50 for that k value of 0.75, right?
Yes.
I'm just confused. You spend a lot of time plotting the profile of velocity out of a nozzle. And then, that's different theta. And the question after this, maximum tilted angle. What's the connection between the two experiments?
From the k
And that
maximum
profile,
angle. Okay, I will show you the calculation.
the relationship between the two.
Okay. Well, it's quite complicated.
Well, I'm waiting.
Okay, wait a minute. Okay, maybe I can draw it to show you. Okay. Wait. Okay. When I tilt it, this is the steam line, and from this,
Maybe you can draw it so that Ajahn Yuk can see.
What?
I can see it. Oh,
Okay.
you can see it.
Sorry. Okay. This is the axis that I point from the center. Okay? This is V1 and V0. V1 and V0 is mean the center of the stream and the boundary of the stream, which is V0 and V1. Well, when we tilt it, if we measure it from this, we will get zeta zeros. The zeta zeros is from V zeros to the axis. And then I want to find zeta 1, because zeta 1 plus zeta zeros will become zeta 2, the maximum angle that we want to find. Well, how K is useful because it's related like this. I get this video into the computer. Then I make a measurement. This is alpha 1, okay, and this is alpha 2. Zeta 1 is the center, is the average of it. So I get alpha 1 plus alpha 2 over 2 will be the position for theta 1. From this, okay, this is wrong, I'm sorry. We know that, how can we use to relate with it is, we know alpha 2 and we know the alpha 2 and we know R. R is measured from this to this. We can get back into the table to find the value of K, and because of that, it will make us predict about the highest maximum angle. Because from this calculation, it's just like inverse, like you know the maximum angle you want to find for K, but if you know K, it also inverse that you can find the maximum angle. Okay. Oh, I'm sorry. Okay, I will present good enough. This is, this is V0, this is V1. Okay. Yes. Okay, I have equation. Wait. From this, K and theta 2. Well, the way to find theta 2 is you should know about alpha 1 and alpha 2. There are two main ways to make the calculation to find the K, and this is the relation between the theta and the K. Yes, then I know this. If I know alpha, I will find the data from the experiment. Alpha, I will find from the experiment. But if I know theta 2, I will find K from the calculation.
Right now you know K and alpha, this week you know K and theta.
Yes?
And what else should we get from the equation?
Oh, sorry, battery is low.
Time is up anyway.